Morning, everyone. Welcome to the third and last day of the conference. This morning session, we're going to be having 3 talks. So the first talk is a plenary, and then we'll be followed by 2 invited speakers. So I'd like to just give a short introduction to our plenary speaker. So it's Prof. Alper Kiraz. He's from the Department of Electrical and Electronics Engineering of Koç University in Turkey. He received his degree from Bilkent University in Turkey, followed by MSCs and PhD degrees from the University of California in Santa Barbara. Then between 2002 and 2004, he worked as a postdoctoral researcher at the Institute for Physical Chemistry at the Ludwig Maximilians University in Munich, Germany. He then joined Koç University in 2004 and became a full professor in 2014. So between 2014 and 2015, he was also a visiting professor at the Biomedical Engineering Department at the University of Michigan at Ann Arbor. And his current research interests include optofluidics and optical manipulation and biomedical instrumentation. So I'd like to welcome our first plenary speaker. Thank you.
Okay. Thank you very much, Angela. Nice to meet you online. So is everything okay? Can you hear me? Can you see my slideshow?
It's all great. We can see your slides really well, and yes, we can hear you. Okay,
yeah, thanks a lot for this kind introduction. And also I thank the organizers for the invitation. It looks like a very energetic meeting, and I wish the best of success to this meeting and to the future meetings. Hopefully will take place face to face, and we will be able to join and drink coffee together. My name is Alper Kiraz. As it was introduced, I am at Koç University Istanbul, and today I will talk about our digital microscopy research, in which we develop our own instruments, also use the deep learning techniques to improve the performance of the instruments, and also to analyze the results that we obtain with our instruments. So we are an instrumentation group. So we are instrument developers in principle, but we are using these deep learning techniques to improve the performance and the analysis of the resulting images. Okay, so this is us, and as it was introduced, I am at Koç University since 2004. It has been a long time. We have done many national and international projects, and currently continuing with other projects. So this is our lab environment. So we are setup builders, including everything like electronic, mechanics, optics, obviously, software, optic alignment. So we do all this on optical tables and design our own instruments and experiments. In addition to this lab environment we are using the central lab facilities at Koç University. We have a newly established nanoscience and nanofabrication laboratory with a nice clean room, 400 square meters closed space. We are using also the Surface Science Center for characterization, SEM, XRD, plasma. We have a medical school at Koç University, and we enjoy very much collaborations with colleagues in the medical school. So we have a research center for translational medicine that facilitates these collaborations. Also, there is an imaging facility, cellular and molecular imaging facility, in which we have many state-of-the-art confocal, multiphoton, STED microscopes, light sheet microscope inside. So I am also one of the responsible faculty members of this facility. So this facility also enables us to collaborate with colleagues at the medical school. We are also collaborating with colleagues at the Energy Center at Koç University. So my group is doing research under 3 main topics. We develop biological and chemical sensors based on optical microresonators, optical technologies. We do microfluidics, optofluidics. We work on droplet generation. We work on developing microfluidic platforms for 3D cell culture that will, in this project, we are trying to grow tumor spheroids starting from tumor cells in a microfluidic chip that we have came up with. And the aim of this project is to develop kits for personalized medicine. So a patient's cells will be given to the chip and they will be grown there, and they will be monitored with different drugs, and the prognosis scenario will be obtained. So we do microfluidic sensing, and also we do, as I said, optical instrumentation, digital microscopes, and also their mathematical improvements and analysis with artificial intelligence techniques. So this third part is the subject of today's seminar. So after this introduction, we can go towards the main topic. So in this talk, I will describe you the instruments that we have developed, and also the techniques that we are using based on deep learning for improving the performance of these instruments, and also for analysis of the images that we obtain. But first, introduction. Obviously, we like very much to use optical microscopes for life sciences research, especially, despite the fact that they have a fundamental limitation of resolution coming from the optical wavelengths that we are using in these instruments. So electron microscopes can give us a better resolution, but we still like to use light microscopes for life science research, mainly because of the fact that we can use fluorescence labeling in this research. So with fluorescence labeling and molecular biology genetics techniques, we can label specific biological molecules of interest in vivo, ex vivo, in a certain scenario, and highlight the specific molecules that we want to study, and study whatever we like, all the dynamics, their locations in the cell, etc. So this fluorescence labeling is a huge advantage of light microscopy, fluorescence microscopy, over electron microscopy, for example, which can in principle give you a better resolution, but without the advantage of fluorescence labeling, and also it cannot allow you to do in vivo studies. So light microscopy is still therefore indispensable for life science research, but we have this wavelength limitation, and it will be good to go over this limitation, Abbe's diffraction limitation. So this is Abbe's diffraction limit. So roughly speaking, lambda over 2 is our limitation. So for visible, 200 nanometers is our limitation. So we have gone beyond this limitation using the super resolution microscopy techniques, and these techniques were subject of the 2014 Nobel Prize in Chemistry. So two techniques were the subject of this Nobel Prize: PALM, photo-activated localization microscopy, and STED, stimulated emission depletion microscopy. So I want to go over these techniques and little bit talk about our setups, and then we will go to deep learning. So I will first mention laser scanning confocal microscopy, as it is still a workhorse instrument, for life science research, and it has been there for a long time. Then I will talk about the structured illumination microscopy, PALM, and STED. Well, we have the Abbe's diffraction limit, and that applies to wide field fluorescence microscopy. Wide field fluorescence microscopy means applying a homogeneous illumination to the sample and imaging the fluorescence coming from the sample with a camera after passing the fluorescence through the emission filters and dichroic filters. So you apply a homogeneous illumination, and that's limited. The resolution is limited by the Abbe's diffraction limit. So these are the formulas, point spread function that give this resolution limitation. Well, confocal principle achieves an improvement over this approach. In confocal principle, we do point-by-point scanning of our sample, and also we use a detection pinhole to eliminate the out-of-focus background coming from the sample. Hence the name confocal. There are two foci, the detection and excitation foci, that coincide, achieved with a laser focusing and detection pinhole. Because of this presence of two foci, we improve the resolution of the wide field fluorescence microscope, okay, using this confocal approach. The disadvantage can be that, well, you need a scanning mechanism because it's a point scanning approach. You need a scanning mechanism, and in principle, that's somewhat slower than the wide field fluorescence imaging, although you can use different scanning approaches, and there are many fast scanners nowadays that enable, live imaging with confocal microscopes. Well, the inventor of confocal microscope is late Marvin Minsky. He invented and got the patent in 1957, even before the invention of laser. So in his patent, he uses a light bulb. So he uses a pinhole also for excitation and another pinhole for detection. And interestingly, after this confocal invention, he moved to artificial intelligence, and he has done a lot of things in computer science, and he was a founder of MIT AI project and co-director of the MIT AI lab for a long time. So this is interesting. I wanted to show this because nowadays we also see a lot of relations, between the super resolution microscopy approaches and AI approaches. So his character also shows a good fit, to what I am describing today. So I wanted to show this. Anyway, okay. So as we said, confocal uses two foci. So therefore, the point spread function is the square of the point spread function you have in wide field microscopy. So when you take the square of the point spread function, it gets sharper. Okay, so you get an improvement in resolution, both in transverse and axial directions. Especially the improvement in axial direction is very crucial. So it enables you to do optical sectioning and record images from different layers of your sample. Well, there are many standard things, and we do this also all the time at Koç University Imaging Facility. You can, this is a Poland, I believe, so you can record fluorescence imaging from different sections of your sample and construct a 3D image, which you cannot achieve with a wide field fluorescence microscope. By the way, I think we will have time for questions at the end, but if you want to interrupt, have a question, please don't hesitate, like to unmute yourself or write something from chat. I will try to answer, so we can make this interactive. I will enjoy that too. Okay, so that's the confocal, and that has been around for a long time. Well, then we have the structured illumination microscopes. So they have been also around for a long time, and we are all working on this as well as confocal microscopy for instrument development. Well, in structured illumination microscopy, we use a structured, as the name implies, structured illumination pattern. So this can be a pattern of stripes, or it can be a pattern of dots. We are using both approaches, stripes or dots. In conventional SIM, you use stripes and you illuminate your sample with 9 different patterns, okay, at 3 different orientations and 3 different phases. That gives you 9 different patterns, and record the images and do post-processing of the recorded images to achieve better resolution. Well, the idea of getting better resolution with structured illumination microscopy can be easily seen in the frequency domain. So if you think of the fluorescence pattern that you record with a structured illumination pattern, that will be in the frequency domain, frequency pattern which is shifted with respect to the wide field illumination case. So because you have a special modulation that enables you to shift the whole frequency spectrum in the frequency domain. So this is something good because your detection optics, including the microscope objective and the camera tube lens, all the things serve as a low pass filter. So there is the highest spatial frequency that can be detected by your detection optics. Okay, this is determined by the Abbe's diffraction limit. So therefore, if there are components in the actual sample fluorescence with spatial frequencies higher than your cutoff frequency, you cannot observe them, in wide field microscopy. But if you shift the whole thing, okay, right, left, then some portions, for example, if it is shifted right, some portions over here, which are actually high frequency portions, now become accessible to your instrument because they are shifted, so they come towards the DC center of this frequency space. That's the idea. Okay, so then you do this in 9 directions. So when you do this in 9 directions, more high frequency components become accessible. So this way you achieve a better resolution. Okay, so that's the idea, and it has been around for a long time, and we have worked on implementations of the SIM technique. What we are working on is to achieve this with LED illumination rather than laser illumination, using a DLP projector, commercially available DLP projector system, which has LED illumination, and also we are using GPU acceleration, for post-processing to speed up the post-processing. Okay, so so these were our goals, well, to achieve super resolution, GPU-based algorithm, and LED illumination. Well, we give these 9 patterns and obtain the modulated fluorescence images, and then recover the high resolution image from these 9 patterns using our GPU-based algorithm. So in this algorithm, you need to do a phase shift estimation of your fluorescence signal. So for that, you go to frequency domain, okay, of the recorded images, and in the frequency domain, you calculate the phase by looking at this shifted spots. So you have to determine first the locations of the shifted spots, and then find the peaks of these shifted spots, and at the peak locations you have to calculate the phase, and also you calculate the illumination frequency. You estimate the illumination frequency again by locating the peaks, these shifted peaks in the spatial frequency domain. So we have implemented this in a GPU-based algorithm. The PhD student Musa Aydın wrote this in CUDA programming with NVIDIA GPU chips. And our implementation, well, first of all, it gave better resolution as opposed to the wide field illumination. So for wide field, here you see 254 nanometers. For the SIM approach, we see 187 nanometers. So we improve the resolution, and also we speed up the whole process depending on the image dimensions, we speed up this post-processing by a large factor, more than a factor of 10, due to this GPU implementation. We also worked on a dot scanning approach in addition to stripe scanning. In the dot scanning approach, you have a grid of dots illuminating the sample, and you move around this grid to cover the whole sample. This approach is called also as image scanning microscopy. Okay, so you have a series of dots, and then you move around these dots. You record many images, this time more than 9 images, 81 images. So this technique is somewhat slower than the conventional SIM. And for each image, for each pattern, you record an image, and what you do is you do a digital pinholing. So you apply a binary mask on top of this raw image. Only consider the fluorescence in the vicinity of the dots that you are exciting. So you do a digital pinholing, scaling, and then summing operations. So this digital pinholing basically serves as the confocal pinhole in the conventional laser scanning confocal microscope. So we have implemented this and obtained the higher resolution, this image scanning microscopy resolution, and also we achieved the higher Z resolution. So on the left, you see the modified, our algorithm, let's say, modified image scanning microscopy algorithm, and this is the wide field fluorescence algorithm. So you can clearly see the improvement in transverse resolution and also in axial resolution. So we went down to 140 nanometers in the full width at half maximum of the microtubules that we recorded, and we tried to make this a compact instrument. This is as compact as we achieved. This is still a work in progress. In this instrument, there is again LED illumination. There is a DLP. So we couple the LED illumination inside the DLP. It goes to the sample. Then we have a camera for recording on the other side. With this instrument, we also are imaging biological molecules in collaboration with Professor Elif Nur Fırat Karalar from Koç University. We are imaging the centrosome proteins. So in conventional manner, you see them as blurred dots, but if you concentrate, they have to be somewhat hexagonal structures. So we are also working on higher resolution biomolecule imaging with this instrument. Well, other two techniques, we don't have contribution, just to give you the information. So the palm technique in photoactivated localization microscopy, what you do is you activate your fluorophores in the sample one by one. Okay, only a few of them are activated at once. Then they are photobleached, then a new cycle begins. So at each activation, following each activation, what you do is you localize each of these molecules. Localization means you record these single molecule images and you find the center of mass of these images. Okay, so that's the localization, and you can, if you have bright enough fluorophores and good enough camera, good enough objective, microscope objective, then you can achieve a localization accuracy much better than the diffraction limit. So we have done this works previously. Here we are localizing some dye molecules and moving the piezo stage step by step, and following the localization together with the piezo motion, you see that we can achieve a localization accuracy of 1.48 nanometers, or 1.48 nanometers with steps of 30 or 20 nanometers in the piezo stage. So you can localize the molecules much better than the diffraction limit. So here also, this is a previous work of ours, dye molecules moving in nanochannels of diblock copolymers. So if you localize the molecules and follow the motion, you can find this nanochannels, the geometry of the nanochannels, and study the confined motion of the molecules inside. So that's the basic principle behind photo-activated localization microscopy. And for photo-activation, you need to activate these molecules one by one. What you use is a second laser and a photo-activated dye molecule. So photo-activated dye molecule in this case can be GFP, and if you give UV light to GFP, you can make it brighter, and stochastically some of these GFPs become brighter, and you can localize them. So this was the technique. It requires a lot of consecutive images to be collected. In the first demonstration, I think it took like 1 day to record all these images, localize the molecules, and reconstruct the whole image. But at the end, if you do this patiently, you get a much more improved image. So you can go down to 20, 30 nanometers in resolution with the palm technique. Is there a question from chat? Okay, no. Well, the other technique is totally different. It is stimulated emission depletion microscopy. So in this case, you use again a second laser for depleting the fluorescence coming from certain portions of your illumination area. So you use this donut-shaped focus for depletion fluorescence coming from this donut. The idea is to make this extension spot, squeeze it basically as narrow as possible by this stimulated emission depletion. So due to this stimulated emission depletion, the fluorophores in this vicinity emit their emission much more rapidly. That's the essence of stimulated emission. So if you do some time gating and ignore that initial phase of fluorescence emission, then all this part will be depleted. So you will end up with only fluorescence coming from the central spot. So this improves the resolution. Okay, that's what Stefan Hell demonstrated. So this is the conventional microscopy. This is state microscopy. Again, 20, 30 nanometer resolutions are achievable. Okay, so nice wrapping up. So we have these nice techniques that can give us much better resolution than the resolution of a wide field fluorescence microscope. Okay, they are very nice. Well, they have disadvantages. Sometimes they are slower. Sometimes they require expensive lasers, so the setups are expensive. But at the end of the day, you can achieve. Of course, still you cannot go to electron microscopy resolutions, but it is very possible, conceivable to go to tens of nanometers, 10, 20 nanometer resolutions with light microscopes. Well, we have these pairs of images. Can we do anything about these? What can deep learning offer to these implementations? Well, before moving to deep learning, I want to just mention this concept of deconvolution analysis to improve the contrast and resolution of images. This has been also around for a long time, before deep learning. So what you do in deconvolution analysis is you have your original image. You know that original image is actually obtained by a convolution of fluorophores point spread functions or fluorophores locations with the point spread function of your microscope. So you know that this is how you obtain the original image. So it is a result of a convolution operation. So therefore, if you carefully calibrate the PSF of your instrument, then you can try to go back and deconvolve the image to obtain a higher resolution image. Okay, so this requires a careful calibration of your PSF in the axial and lateral directions. But if you do that, then you can use these software approaches to improve the contrast and resolution of images. And this is a reality, and there are software packages that achieve this approach. So this is a mathematical approach, so it is possible. Well, you can also think and implement this using deep learning. Okay, now we move to deep learning and what can this offer to us? Well, in deep learning, we go to a black space, for me at least, because it's a new space for me. We have some neural networks. Okay, so there are neurons, and these neurons are connected, and each connection has a weight function. Okay, so using these neurons, you establish a network. Okay, and this whole network has an input and output. This input can be image or one-dimensional vector. Output will be your image or one-dimensional vector. So you can use this network to extract the features, all the features, higher level features of your vectors. And you can train this network such that for a given input, it gives you an output. So you obviously need a lot of data to do this training. So you need a data set of pairs, just like these pairs, you know, input, ground truth, input, ground truth. So input is the low resolution input, you can imagine, and ground truth is like the deconvolved output of your instrument. So what your instrument actually should give at a higher resolution. So once you have such many pairs of images, use the low resolution ones as your inputs and high resolution ones as your ground truths. Using these pairs, then you can train this network. Okay, so training this network then becomes equivalent to extracting the PSF function of your instrument. So it is like a calibration operation. Okay, the good thing is you don't need to be very, let's say, careful and precise in this calibration operation. You just need to provide data, okay, blindly. You provide all this data which are collected from this instrument, many data as input and ground truth, and you do the training. And as a result of this training, the connection weights are adjusted and optimized, and this learning has been achieved. This learning scenario that I described is called unsupervised, which means you just provide the input and ground truth. You don't do any additional processing, or the expert doesn't do any annotation on the ground truth. It can also be supervised, okay, for other scenarios. Well, if you have images, for example, an expert can take the image and draw a line around the dog, for example, and indicate this portion of the image as a dog. Okay, so this is supervised. So the supervisor has indicated these pixels as the location of the dog, and this is also called image segmentation. So you classify this as a dog, and also you segmentate the locations of the pixels belonging to the dog. Okay, so that is a supervised learning scenario that you can use for image analysis. The previous one was an unsupervised learning scenario that you can use for improving the resolution of your instrument, just like the deconvolution approach. Well, we are working on this, and I will now discuss the works in progress. So both instrumentation performance improvements and also image analysis aspects. So for performance improvements, as we said, you give an input and ground truth. Input is a low resolution, ground truth is a high resolution. So input ground truth pairs can be also obtained by different exposures of your camera. For example, you can use low exposure for noisy data, high exposure for less noisy data. So low exposure, high exposure, low exposure, high exposure. So this way you can train a network, and using this network afterwards, you can acquire images with a low exposure, but improve their signal to noise by result of this neural network training. Okay, so we worked on these. Well, we are also working on the confocal and structured illumination microscope outputs. So we collect this data and train our networks. Here we have a work on line scanning confocal microscopy. In line scanning confocal microscopy, what you do is you illuminate your sample line by line in a consecutive manner, and you use a rolling shutter camera for detection. Rolling shutter camera detects also line by line, so it serves as a digital pinhole in one dimension. Okay, so it is working as a confocal in one dimension. The other dimension still doesn't reject the background, but the vertical direction rejects the background. So this is called line scanning confocal microscopy. It's a tiny little instrument that you can build. So we built it using again a DLP projector, and acquired pairs of images with the line scanning mode and solid white, which means total illumination mode. So we improved the resolution and contrast in these pairs of images, and then used neural network architectures, convolutional neural network, or generative adversarial network GAN architectures, and achieved improvement in contrast. Okay, so this is the input of the network, ground truth that we used, and output of the two neural networks. So the contrast parameters are here. So for input 0.26, ground truth 0.40, and output of CNN 0.38, output of GAN 0.38. So using the machine learning, deep learning network, we can improve the contrast of the input and make it close to the ground truth contrasts this way. Okay, so and we are also doing bioimage analysis, especially we are doing cell counting and cell viability analysis. So for this, we have images of cells recorded with a low magnification microscope, and the task is to identify individual cells and report the number of cells in a given image. Also look at the contrast of these images and identify the dark ones as dead, the bright ones as alive cells. Okay, so this is the cell viability analysis, and this contrast is generated with a contrast staining agent such as methylene blue. So this is a very general technique that is used for all the cell studies. So in any like cell laboratory, you have you need to do cell counting. So you need to monitor the growth of your cells, the progress of your cells, and conventionally this is done usually with an operator, with a counter, manual counter and a counting grid. So at each grid square, the number of cells is counted visually, and you can appreciate if this number is big, there is a big room for error because this is a operator. You can automate this whole process with deep learning. This is what we have done. So for this, we have, and also you have to take into account the class of the cells. That's another problem. For this, we have established a modular deep learning system that consists of 3 main modules. The first module being the segmentation module. Okay, so you give the image to the first module, and as a result of this image, you obtain a binary image of segmented cells. Binary meaning only black or white. And then some cases can give you clusters. So we make a check in the second module. We make a check for clusters. And if it is clusters, we do circle detection, detect circles inside the clusters as cells. If it is not clustered, then these are single cells. So these binarized images go through the cluster check, and they are further separated into individual cells, and then they are fed to the viability analysis, where their contrast is checked. If the contrast is bright, so if they are bright cells, then these are live. If dark, they are dead cells. So we have established such a 3-module system and worked with the system. So you see some ground truth inputs and results of our segmentations. At the end, we achieved a good accuracy for cell counting, nearly 97% accuracy. For the viability analysis, nearly 99% accuracy with our algorithm. So obtaining better than 95% usually is sufficient. The 95% is like the benchmark threshold that is achieved with other products that are used in the labs. So these numbers are quite satisfactory for us. We are now working on this with different also cell cultures, not only one type of cell culture, but also with other cell cultures. So we are collaborating with Professor Ömer Aydın from Kayseri Erciyes University, Musa Aydın and Berna Kiraz from Fatih Sultan Mehmet Vakıf University in Istanbul. We are also doing brain vasculature analysis. So in this case, you have images of brain vessels recorded from lab animals. These are fluorescence images or multiphoton microscopy images. The task is to binarize these images, again, to find out the locations of blood vessels in these images. Okay, so these are the original images, and these are the ground truths. That is the task. So you will give me your fluorescence image. I will binarize this image and give you the image of blood vessels. So this is what we are doing. For this, we have first annotated this data. Okay, so many such images have been labeled literally, like manually, like paint type of a program by our graduate student. So these blood locations have been indicated. So we established the ground truth series of images. So then we have this pair, okay, the input and ground truth. This pair has been used for training of different neural networks. For neural networks, we use different geometries or architectures available. This UNet architecture, modified version UResNet architecture. Also, we have used this architecture UNesNet, which is a technique that gives you training and segmentation performance with less computational cost. Okay, so we used also that architecture. So you see the computational cost here in the flops. In one case, we have 436 G flops. In the other case, 84 G flops. So we can reduce the computational cost with the second algorithm by not sacrificing from the performance of segmentation. So we are using these architectures, and we are able to segmentate the blood vessels. And after this segmentation, we will form the 3D geometries of blood vessels and do brain vasculature analysis. Okay, in this vasculature analysis, you analyze like vascular area fraction, length of blood vessels, number of branches, nearest distance. You look at such parameters, and you study neurodegenerative diseases such as SMA, ALS, or Alzheimer's disease. So we do this in collaboration with our medical school, Professor Atay Vural from medical school. And in the future, we want to go to three-dimensional segmentation, not only 2D. These are actual slices of a 3D image, but we want to do segmentation also using 3D operations. And also we want to develop a user-friendly application that can be used by a normal life science researcher, easily usable, deep learning based application. Okay, so I can end at this point. I hope I am not late behind the schedule. So, well, this whole thing is also new for me, like 2-3 years of history is what I am talking about here, but it's very exciting. So you can use deep learning to many things in optical microscopy, it seems. Improve your instrument performance, do a lot of bioimage analysis, and doing this is not terribly difficult, like to my experience, because there are many libraries, many things, all these networks are available, with the Python programming language, they are all available. And also, you don't do many pencil and paper type of calculations, like you don't need to calibrate PSF, do this, you just need data. Okay, you can go to lab, collect data and try to see some outcome. From that respect, it's an interesting research. It's a quite straightforward, in a way, research, but it's a powerful research. I want to finish with this note, and this is the group, and thank you for your attention.
Thank you. Thank you very much for the wonderful talk. It has very notable causes, investigations that you can use it for. So I really like the medical applications that it has. So do we have any questions? And let me just check the chat quickly. Okay. So I don't see any questions in the chat. Would anyone like to unmute themselves or raise their hand and ask a question? So I think there's a clapping hand and maybe not a raised hand. There is a question. Yes, so there is a question. Someone has posted they can ask a question in the chat. Yes, please go ahead and unmute yourself.
Güneş Kaya, I think. Okay, you can
they can't unmute. Sorry.
You cannot write. You can write from chat if you like, or you can write me an email later.
No, I'm wondering.
Now is okay.
Oh, okay. Oh, the organizers have unmuted you.
Where are you?
So I think so. Whoever asked the question in the chat, you should be able to unmute now.
Hello, can you hear me now?
Yeah.
Okay. First of all, thank you, Professor Kiraz. It was very grateful to listen your detailed presentation. Actually, I've graduated from Koç University also, from mechanical engineering. So it's very happy for me to see you again. I was graduated in 2007, actually.
Okay.
I have a small question. So you talked about the neural networks and you talk about the training part. And yes. I wonder if that training and the training of the neural network is dependent on the instrument itself. I mean, when you apply the data for a specific instrument to the neural network,
yes,
the outcome and the total trained network would also work for another instrument.
No, that's a great question, Güneş. Yeah, that's the problem. Each instrument, just like calibrating a PSF, each instrument will have its own characteristic. So you have to train for that specific instrument. So if you look at it that way, then you can ask yourself this question. Well, if I need the image pairs, if I need the high resolution image for training from each instrument, then it means that actually I need that high resolution instrument somehow. So yeah, this is a question mark. So making this instrument independent, I think is a big challenge. And is not clear at the moment. So there are a lot of demonstrations in the literature. You know, obviously this whole thing will work very nicely for a given instrument. So I can work my own instruments in which I can record the image pairs without a problem and do the training and show that everything works. Okay, it's all okay. But you cannot use the trained network of my instrument in another instrument, or it's not trivial. So this should be really carefully handled. And once this is achieved, then it will be a great breakthrough, I think. Also, I mean, it's already at a good stage, but making this instrument independent is not straightforward at this stage. It's a great question.
I see. Thank you. Even if it is the exactly same instrument, if the calibration shifts, does it cause a problem for the?
It can cause a problem. Yeah, I know what you mean. It can cause a problem. So but we didn't study the sensitivity. I am just responding with my feelings at this moment, actually. But I mean, everything is so data sensitive. So yes, all these should be carefully studied.
Okay. Thank you. Thanks.
Great. Thank you so much. Just due to time, because we're running a little bit over, I'd like to thank the speaker again. And if there are any questions, I'm pretty sure we can post them in the chat, and Prof. Karaz will be more than happy to answer them. So thank you very much.
Thanks a lot.
Thank you.
Bye.
So our next speaker is an invited speaker. It's Dr. Zakar Kudrysinski. Hopefully I've pronounced your surname correctly. You can correct me. So he is based at the University of Nottingham in the UK. He received his PhD from the National Academy of Sciences in Ukraine before moving on to the UK, where he's continued his research in layered semiconductors. So please take it away. So I'll stop my camera.
Hello to everybody. I'll try to share my screen now, my presentation. Please let me know if you can see.
So we can see your slides. It's just not in presentation mode yet. Now it is. That's great.
Okay, yeah, great. Yeah,
it looks good.
Yeah, thank you. Thanks. Just a sec. Okay. So hello again to everybody. My name is Zakar Kudrynsky. I'm a postdoctoral research fellow at the University of Nottingham, United Kingdom. And thank you for inviting me to give this talk. It's a great pleasure to meet online all of you. And it is also a great pleasure to tell you about the work that I have been doing in the last several years that focuses on a specific semiconductor van der Waals crystal called two-dimensional indium selenide. I'm going to tell you about all different aspects of research on this material that I have conducted with my colleagues during the recent years. The focus, the focus is on this crystal, 2D indium selenide. 2D indium selenide, which is now considered as a very promising semiconductor, the next silicon. Maybe this is too provocative, but I'll try to convince you that this is really an interesting material with an interesting fundamental physics, and also because of a number of possible applications. I'm aware that not everyone in the audience is familiar with 2D materials, so I'll give a brief introduction to this particular class of materials, and then I will focus specifically on 2D indium selenide. I will also show you how this material can be combined with other 2D crystals to form the so-called van der Waals heterostructures, where we can explore new exciting physics. Importantly, I'll show you how the structures that we have been developing and studying with my colleagues can be used in various functional devices and technologies. And I'll complete my talk with conclusions and outlook. So there is a wide range of van der Waals crystals. More than 1,000 of them are known so far. And what is common for all of them is that they consist of separate layers weakly bound together by van der Waals forces, which make these systems naturally favorable for miniaturization to create truly 2D crystals. Separate layers with the thickness down to 1 atom can be isolated, still preserving very good crystal structure. And our attention is attracted to this particular group of crystals called metal chalcogenides, with a specific focus on this particular one, indium selenide, which is a relatively new addition to the library of 2D materials. So I start with gamma polytype indium selenide, the crystal that has been known in its bulk form for many decades, and in fact since the 1930s. But 9 years ago in 2013, me and my colleagues have rediscovered it as a 2D material with new exciting properties. This is an example of the crystal structure of gamma indium selenide. The unit cell has 3 layers with ABC stacking. It consists of separate layers that are weakly bound together by van der Waals forces. But within each layer, the atoms are bound by covalent forces. Here you can see a single stoichiometric layer with a thickness of just 0.8 nanometer, and it consists of 4 layers of indium and selenium atoms. In the bulk form, it's a direct bandgap semiconductor with a gap in the near infrared region and high electron mobility. I started working with this material as a PhD student in Ukraine. There we were doing growing these bulk crystals of indium selenide by the Bridgman method. And then in collaboration with colleagues from Nottingham, we started mechanically exfoliating these bulk crystals down to few layer nanoflakes. And what we observed is that this material that in this material, the optical gap strongly depends on the layer thickness, as we go from relatively thick flakes of about 20 nanometers to just few layers. We studied hundreds of flakes of different thickness and found these dependence a strong energy shift with layer thickness that can be reproduced by a simple curve, a simple effective mass quantum well model. In this crystal, the effective electron mass is so light that when we exfoliate this material down to thinner and thinner layers, the 0 point energy of the electrons increases, and this increases the band gap, which is shown here. This result was then confirmed worldwide by different groups. Also in a joint work with Professor Andrew Geim from the University of Manchester, a Nobel Prize winner. So indium selenide remains optically active, even with a thickness of 1 layer. So you can see that there is this tunability of the optical response in a wide range of spectrum, from near infrared to visible and UV. And this tunability is significantly larger than in other systems. So I have just shown you that it's an interesting material optically, but it has also a high electron mobility, higher than in silicon, and one of the highest within the family of 2D van der Waals crystals. And that manifests through the observation of the quantum Hall effect in very thin layers. This contribution, this combination of 2 important properties, tunability of the bandgap and high electron mobility, is very important for a semiconductor, and led Andrew Geim to comment that ultra-thin indium selenide represents a golden middle between silicon and graphite. Since this early work, we learned more about this class of 2D materials. It was important to understand not only how the properties of indium selenide change as we go to thinner and thinner layers, but also to get a deeper insight why this happens. And theoretical modeling of the 2D band structure of indium selenide by density functional theory, which was done in collaboration with Professor Vladimir Falco from the University of Manchester, and his colleagues brought light onto that. So we can start, for example, with 10 layers thickness, and look how the energy dispersion is changing as we make indium selenide thinner and thinner. The conduction and valence bands are at gamma point, but as we thin the layer, the valence band shifts. So as we go to a thinner layer, you see the band gap increases, but also the valence band changes significantly. The gap opens and more, and we increase as we increase the number of layers, as we decrease the number of layers. And finally, the valence band is significantly changed for a single layer. The valence band shifts away from gamma point and the crystal becomes indirect. Another important aspect of here is that it has been also explored recently. This is a possibility of combining this 2D material, indium selenide, with transition metal dichalcogenides, as the two systems have quite different electronic band structures. And here the idea is to engineer type 2 interfaces by assembling atomically thin layers of indium selenide with transition metal dichalcogenides to create an interlayer exciton with electrons that are at the conduction band edge of indium selenide and holes that holes in the transition metal dichalcogenides that are also confined at gamma. And this enables a creation of an exciton without any momentum mismatch. And the excitons that also have tunable energy, an energy that can be tuned by choice of layer thicknesses, as shown here, for example. Different excitons can be created by using, for example, 4-layer indium selenide with different layers of TMDCs based on tungsten disulfide. And this idea of interlayer excitons has been tested experimentally in collaboration with Professor Alberto Morpurgo from the University of Geneva in Switzerland. So the unique electronic band structure of indium selenide can be used in many different ways and in combination with different materials. And one of the interesting combinations of materials is also indium selenide and graphene. So why indium selenide and graphene? What is so special about these two materials together? Well, it has an interesting band alignment for a range of layer thicknesses. The conduction band edge of indium selenide is close to the neutral point of Dirac cone of graphene. And this means that we can explore the charge transfer between graphene and indium selenide by different methods. By electrostatic gating, by moving the Fermi level up and down, and also by light illumination. So we started with electrostatic gating, and the idea is the following. You have an indium selenide graphene heterostructure on silicon dioxide, and so you gate through silicon, and you can identify two distinct gating regimes. One of them is where the Fermi level is in the forbidden gap of indium selenide. If you are using n-type indium selenide, you have this type of alignment with some depletion at the interface between graphene and indium selenide. But from the point of view of moving the Fermi level, the graphene behaves effectively like crystalline graphene because there are no states to fill the gap of indium selenide. And then you go to this another regime, which is more interesting when the Fermi level starts approaching either donor states or the high density states in the conduction band of indium selenide. This regime is where you have charge redistribution between the two layers. So we started electrostatic gating in this type of structures. These are hole bars made of CVD or exfoliated graphene. Part of the hole bar is kept with an indium selenide flake. The two parts of the device are in series resistance configuration, so we can pass the same current and look at longitudinal resistance and hole resistance. So we did it, and what we noticed is that the two parts of the device tend to have distinct behavior. In one case, where the graphene is kept, we see this large quantum hole plateau. This is at low temperature and extends from a few Tesla up to 20 Tesla. Later on, we extended these measurements to high field to 30 Tesla, and the plateau is still there. But it is also quite robust. It is observed nicely up to the temperatures of the order of 200 Kelvin. And this effect is observed when the Fermi level starts approaching the conduction band and donor band states in the indium selenide. And because of the high density of states, you have a pinning of the level. This extended plateau persists at high temperature. And these states close to the conduction band edge have high binding energy. We measured these donor states in the system, and we measured the binding energy of the order of 30 milli-electron volt. So this shows that we have a good charge transfer between the two layers, which we can also probe by light. So now in this experiment, we have a similar structure to the one that I showed you before. Here we have a conducting channel and an encapsulating layer. So indium selenide is the optically active layer. So we can look at the whole resistance versus gate, but also in the dark and under illumination. And you can see that under light illumination, we can change the sign of the whole resistance. By light illumination, we can effectively change the electron density in the graphene, going from hole type of conductivity to electron type of conductivity. So this also changes the resistance. We can see that the change in resistance under light is not affected much by temperature. It persists both at low and room temperatures. So now we can learn from this study and try to make photodetectors based on this effective charge transfer and based on good electrical and optical properties of the layer. So we can use different types of geometry. In this device that I have shown you, indium selenide was an optically active optical channel, and graphene was a conductive channel. But here we have also studied other structures where indium selenide acts both as optical and conducting channel, and graphene serves as transparent electrodes. Graphene make an ideal electrical contact to 2D indium selenide, better than any metal. So we have explored devices of both planar and vertical geometry. For example, this is a planar geometry where we have a flake that is on two graphene electrodes, and there are regions with partial overlap between the two layers, and there is a gap between the two graphene electrodes. So we can look at the photo responsivity of those devices. We obtained good photo responsivity even without any externally applied electric field. In other words, we see photovoltaic effect due to this bending at the interface. We can operate these devices in the photovoltaic mode, and they have very high responsivity. The high photoresponsivity arises from the fact that the electrons can cross this gap very quickly as a high mobility electrons. And the photoresponse is mainly controlled by the ratio between two times: the transit time of electrons that is short, and the lifetime of the holes that is very long. And we also look, and we also looked at other geometries, which is a vertical geometry. So rather than to have two graphene electrodes in plane, we have a top and bottom graphene electrodes. And in this case, a PN junction we can realize a detector that works without any applied bias, basically self-powered due to the built-in electric field by this junction. But this vertical structure is interesting not only because of the possibility of photosensing, but also of generating light. So recently we have been looking at the electroluminescence in this type of geometry. I also want to give you an overview of other heterostructures that we have been looking at recently, starting with a resonant tunneling field effect transistor, where you can see an indium selenide layer is embedded between two graphene electrodes, the source and the drain. Here we have studied the resonant transmission of an electron through a 2D subband in indium selenide, and observed these regions of negative differential resistance in the current voltage characteristics that can be tuned by the Fermi level in the graphene source. We also developed this type of structure, which is a tunnel field effect transistor that combines black phosphorus and indium selenide. In this case, we formed a type 2 interface, a sort of Zener tunneling, and look at band-to-band tunneling across interface between black phosphorus and indium selenide. And in this case, we observe also negative differential resistance tunable by gate. We have also developed and fabricated a number of PN junctions with type 2 band alignment, combining indium selenide with other materials. For example, heterostructures produced by controlled oxidation of indium selenide to form P-type indium selenide and type indium oxide junctions, or mechanically by a dry transfer of flakes of other van der Waals crystals on indium selenide, for example, gallium selenide. And these p-n junctions have a number of useful functional properties, such as rectifying behavior, broad photoresponse in zero bias, and electroluminescence at room temperature. So I have shown you in my presentation that 2D indium selenide has opened promising directions in science and technology, especially in optoelectronics, but its thermal properties should be carefully considered and tailored for specific studies and applications. Previous studies on bulk indium selenide showed that it has a relatively low thermal conductivity, which is also highly anisotropic due to the layered crystal structure. This low thermal conductivity originates from the heavy indium atoms, but little is known about thermal transport in the 2D layers. Theoretical atomic displacement studies showed that whereas optical modes are mostly confined within indium selenide layers, acoustic modes that dominate the heat transport are spatially delocalized within different van der Waals layers, so they are more strongly affected by atomically thin layers. The problem with the currently available theory is that it ignores a few important things, such as heat transfer across the interfaces, lateral boundaries, and phonon scattering by impurities. An experimental investigation of heat transport at nanoscale is challenging as it requires advanced microscopy imaging techniques. To probe the thermal transport of 2D indium selenide with nanoscale resolution, we use a scanning thermal microscopy. These studies were conducted in collaboration with the National Physics Laboratory here in the United Kingdom using their home-developed setup. We have a scanning probe, which is basically a microscopic object with a nanometer size radius. Our resolution is actually the radius of this probe. The probe is a metal device which is heated by electrical current, so it gets hot. The probe is a part of a Wheatstone bridge. When this hot probe is in touch with the sample, we have heat transfer. The temperature of the probe drops, resistance decreases, and we have an unbalanced bridge. To balance it again, we need to change voltage on the bridge, and essentially we will be measuring drop of voltage as a signature of difference of thermal conductance of our sample. So important to know from all that is that our thermal conductance is inversely proportional to the change of output voltage on the bridge. These techniques allow studying heat transfer at the nano and micro scale. In contrast to far field optical techniques such as Raman spectroscopy, STHM is not limited by optical diffraction and can image the thermal response of a sample with spatial resolution down.
Not responding.
Sorry?
Sorry, I think someone was unmuted. I've quickly muted everyone. Oh, hang on. Sorry, I've accidentally muted the speaker. Sorry. Okay, great. Sorry. You're good. Apologies.
Can I continue?
Yes, please go ahead.
So importantly to know from all that is that our thermal conductance is inversely proportional to the change of output voltage on the bridge. And an optical image here shows an exfoliated, our exfoliated nanoflakes of indium selenide on a substrate, and this is the STHM tip with a probe. So here on the left, you can see an AFM image of an exfoliated indium selenide flake on a silicon dioxide substrate, consisting of two parts, 5 layers and 1 layer. On the right, you can see a corresponding thermal image. It shows that when the heated tip touches the silicon dioxide region, it gets much colder because silicon dioxide is thermally conductive, and thus it dissipates heat from the tip. In contrast, when the tip moves to indium selenide, it remains relatively hot, which indicates that the flake does not conduct heat well. As the result, in the thermal map shown here, both parts of the indium selenide flake appear red-orange, indicating the ability of indium selenide to dissipate heat from the STHM tip, that it is lower than that of the dark blue colored silicon dioxide. This is quite an unexpected result, as in bulk state, indium selenide has a significantly higher thermal conductivity than silicon dioxide. And here we see the opposite effect in the 2D state. So this anomalous funding contrasts with previous theoretical studies in the literature, where the role of the substrate was not taken into account. The ability of 2D indium selenide to conduct heat depends on the thermal interfacial resistance between indium selenide and the supporting substrate. And an STHM profile shown on the right illustrates the measurements done for 5-layer and single-layer parts of the flake, and reveals the thermal conductance. The thermal conductance only weakly depends on the layer thickness. I'll come back to the thickness dependence later in my talk. To investigate the size dependence further, we studied systematically hundreds of flakes with different area, shown here in the thermal image. We plotted, the plot here shows the STHM response as a function of area for samples with more than 15 layers. We can clearly see that the thermal conductance decreases drastically for laterally small flakes with an area of less than 2 square microns. To explore the thickness dependence, we examined indium selenide flakes with area of more than 4 square microns and thicknesses ranging from 1 to 100 layers. The choice of relatively large area flakes avoids conflating dependence on thickness with dependence on the area. This study shows that the value of the output voltage is similar for flakes thicker than 10 layers, but doubles in few layer flakes, indicating a reduced thermal conductance in atomically thin layers. This effect is quite anomalous and is experimentally reported for the first time, but is consistent with earlier theoretical studies. The graph here compares our experimental dependence of the thermal conductance on the flake area with calculated dependence from early theory work. And you can see that there is a good agreement here. We can explain this by taking into account side-dependent phonon transport, namely by attributing the observed effect to phonon boundary surface scattering and to the modified phonon dispersion due to quantum confinement. The phonon coherence length tends to decrease proportionally with decreasing thickness, and phonon modes change only in few-layer indium selenide. Apart of that, there are other important factors contributing to low thermal conductance, including phonon scattering due to impurities such as indium interstitial atoms in our crystals. Also, the interface of 2D indium selenide with the supporting substrate can play an important role. The two interfaces interact elastically via van der Waals and Coulomb forces, and due to strong dependence of the potential energy on distance, the increase in the separation between the layer and its supporting substrate caused by an imperfect interface, ionized defects, and large electron-phone interaction in indium selenide can change the ability of phonons to be transmitted across the interface. Our previous studies of coherent phonon transport by picosecond ultrasonics revealed large regions of up to 10 square microns of so-called broken interfaces, where the indium selenide layers are weakly coupled to the supporting substrate due to surface roughness of silicon dioxide and contamination at the indium selenide silicon dioxide interface. So a thermal coupling between indium selenide and silicon dioxide is reduced, causing an interfacial thermal resistance and suppressed heat dissipation from the flake. To assess further the role of the substrate, we have investigated freestanding indium selenide flakes, as well as flakes supported by different substrates. Here we transferred indium selenide flakes on microwells in silicon dioxide. An AFM image here shows a flake that is partially freestanding and partially supported by the substrate. And here we have a thermal image of the same area. We can see that the STHM probe when the STHM probe is over the freestanding region, it is cooler. This actually means that indium selenide disperses heat here better than indium selenide on silicon dioxide. The reduced heat transport in the substrate-supported indium selenide is attributed to phonon scattering by interface defects caused by surface roughness and contamination. There is also another important effect here occurring at the edges of the microvalves. As we look carefully at the thermal images, the edges appear as bright yellow rings, indicating a lower thermal conductance compared to the substrate-supported freestanding regions of indium selenide. While this could be a topographical artifact due to decreased contact area between a tip and the surface, it can also arise from the localized decrease of conductance due to a strain effect. At the edges of the microvalves, the flake is bent and thus subjected to tensile strain. This assignment is confirmed by our micro-Raman spectroscopy studies, revealing a Raman redshift of the vibrational modes at the microvalve edges. Previous studies showed that tensile strain in bent indium selenide can shift these Raman modes and enhance anharmonic phonon scattering, reducing phonon group velocity and heat capacity. The choice of the substrate often means to modulate the thermal response of 2D material. We investigated indium selenide flakes on different substrates with low and high thermal conductivity. Here we transferred flakes on a periodic array of PMMA micropillars on a silicon dioxide substrate. PMMA has a very low thermal conductivity. We can see that our probe is getting hotter in the region where indium selenide is on PMMA than on indium selenide on silicon dioxide. So it means that by using a material with low thermal conductivity as a substrate, we can reduce the ability of a 2D material to dissipate heat and thus reduce its thermal conductance. This lower heat transport is a limiting factor in the thermal management, but can be beneficial for thermoelectrics, where materials with high electrical conductivity and low thermal conductivity are needed. It should be also noted that PMMA is widely used in device fabrication of 2D materials, and the remaining residues can substantially distort thermal transport, leading to overheating. In contrast to this, an enhancement of thermal conductance would naturally be expected from a material with high thermal conductivity, such as hexagonal boron nitride. However, our studies did not reveal any significant increase in thermal conductance compared to indium selenide on silicon dioxide. This unexpected result could potentially originate from thermal expansion mismatch and or rotational crystal misalignment. Also, we cannot exclude the possibility of contaminants being trapped between the van der Waals flakes during the polymer-assisted fabrication, which could cause a perturbation of interface coupling.
Sorry, we've got about 2 minutes left. Okay.
Yeah, so let me conclude now. I hope I've convinced you that indium selenide is an interesting semiconductor system, thanks to its unique band structure, tunable absorption, and high electron mobility. We successfully exploit these properties of indium selenide in a range of functional devices, in particular photodetectors, with high, broad, and fast photoresponse. The results suggest that this system could be a good platform for applications in photonics and electronics. In addition, anomalous low thermal conductance is favorable for 2D indium selenide-based thermoelectrical technologies. With this, I would like to finish my talk and acknowledge my colleagues from Nottingham who have contributed to this work, the professors, the postdocs, and PhD students, but also the success of these activities would not be possible without fruitful collaboration with several groups in the United Kingdom and worldwide, including very useful links with the University of Manchester, the National Graphene Institute in the UK, as well as Chernivtsi branch of the Institute for Problems of Material Science in Ukraine and European Magnetic Field Laboratory, and many others. So thank you very much for your attention.
Thank you so much for the very interesting talk. Are there any questions? Let me quickly check the chat. You're also welcome to raise your hand or just post in the chat, and I'm sure I can find where to unmute people. So I just have a quick question. So this material, this indium selenide, is it currently already used in electronics and that? Are there devices that we
Not yet. So it's currently still not used, and the reason for that is that we still haven't managed to produce it scalably as ultra thin films. So we need to develop epitaxy deposition techniques to basically make this technology scalable, and we are working now on that using molecular beam epitaxy.
Okay. Wow. Okay. Well, if there aren't any questions, I'm sure if you think of any questions, please just post in the chat. And I'd like to thank the speaker one last time. Thank you very much for the interesting talk.
Thank you.
Let me just open. So our next speaker is also an invited speaker. It's Prof. Valery Tuchin. Hopefully I've pronounced your name correctly. And he's from the Science Medical Center in Saratov State University. So he's the head of the Department of the Optics and Biophotonics Department and the director of the Science Medical Center at Saratov University. He's also authored over 1,000 articles, published numerous textbooks, and has over 70 patents. So welcome, we're really excited to hear your talk.
Good morning, everyone. Do you hear me?
Yes, we hear you very well.
Yeah. So I would like to demonstrate my screen. One second. Do you see my screen?
Yes, we do. So I can see your screen. It's just, yeah, it's not, not in presentation mode yet though.
Yep. 1 second. Is it full screen?
Yes, now it is.
Yeah, good. And listed.
Great. It's all looking good. So
yeah, good.
Yeah.
So good morning once again. First of all, I would like to thank organizers for inviting me, and it is great pleasure and honor for me. And my presentation will be maybe quite different from the previous one, and I will talk about the tissues, optics of tissues, and how to make tissues more transparent for light in order to provide any kind of imaging like optical coherence tomography or multiphoton microscopy and some fluorescence imaging and some other technologies which are very, very popular in biophotonics. So first of all, I would like to introduce my university. This is a campus of Saratov State University, which we are sharing with the Saratov Medical State University. And also I'm very proud that the first cosmonaut Yuri Gagarin studied at a technical school near my apartment when I was a boy. And a few years later, on April 12 in 1961, landed near Saratov. So you see here the outline of my talk. I will try to be in time and to present some basic data on optical clearing and then some interesting examples to show. So the idea is very simple because any tissue is highly scattering tissue. So scattering coefficient is huge, especially in the ultraviolet. And normally scattering coefficient in the visible light and near infrared light 10 up to 100 times bigger than the absorption coefficient. You see here, this is absorption coefficient in the visible light. I would like to talk about the ultraviolet part of the spectrum and also about the terahertz. And you see here that the scattering is huge here, and for terahertz range, absorption is huge. So if we find some agent or some liquid which can be impregnated into the tissue, like here, you see here some drop of the clearing agent. So if it degrade tissue, dehydrate, not dehydrate, but dehydrate tissue, and equalize the refractive index to match the refractive index of the scatterers. In that case, we can get both reduction of water content, so absorption in the terahertz range, because this is a water absorption, red curve. This is the water absorption, which is the main chromophore in tissue, because in soft tissue, it's about up to 80% of water. Therefore, the penetration light into tissue and also the blurring of the images depend on the water content in tissue, both due to refractive index mismatch and also due to absorption. Indeed, absorption and scattering can be enhance each other, because if you have a longer pathway for photons in absorbing or slightly absorbing media, like in tissues, it is this absorption is enhanced due to longer pathways of the photons which are traveling within this tissue. How to describe it? In the framework of the ME theory, you can write a simple equation for reduced scattering coefficient, which are depends on the real scattering coefficient and the anisotropy factor of the scattering. So anisotropy factor showing us how photon travel after the single individual scattering. And for tissues, for many tissues, soft tissues, the factor is close to 0.9. So this is highly anisotropic scattering. And this scattering parameters depends on the refractive index mismatch of the scatterers, like part of the cells, like nucleus, like other organelles. And if we equalize refractive index of the background of the interstitial fluid around the scatterers, like fibers or some, as I said, mitochondria and other organelles. If we can equalize this, we can reduce significantly scattering, because it's squared, you see here, and therefore we can do tissue or any scattering media more transparent. So how to do it? So if we use some hyperosmotic agents like glucose, sorbitol, glycerol, all of them are biocompatible. Also, we can use some X-ray contrast agents or MRI agent contrast agents. Also can provide some refractive index matching. So they are both can work both in optical for optical imaging and also for MRI or X-ray imaging. So you see here a few examples how to do the tissue more transparent, like this eyeball. After a few drops of the propylene glycol, you see here retina, no scattering of sclera. The same for cerebral membrane. You see here nothing seen here after a few drops, because we provide refractive index matching and dehydration of this tissue. Also, it can be done for big samples like a rat or mouse brain. You see here that it became transparent. But for this procedure, because the diffusion of clearing agent behind this technology, that means that you need minutes here for thin tissue, and for thick tissue you need some hours or days to provide this. So indeed, in order to impregnate or deliver this clearing agent into tissue, like this one, this is optical clearing agents, typical optical clearing agents, you need some enhancement, which are very, very developed area in the cosmetology and drug delivery through the skin and some other biological membranes. You see here chemical enhancers, physical enhancers like iontophoresis, ultrasound. Also, you can use some carriers uploaded by the clearing agent together with the drugs, because the final goal of study is to see something inside tissue like a tumor and deliver clearing, together with the clearing agent, deliver some drug for treatment. So also biological enhancers also available. So this is some simple, more or less simple instrumentation which can be used to demonstrate optical clearing and also to use it in the real clinical or biological application. So collimated transmittance, this is sample, one beam here or broad light beam here, some detector spectrometer here. You can provide some simple measurements. Then you impregnate your sample with the clearing agent, and it in a few minutes became more transparent and showing us some specific features of the structure of this tissue and so on. So if you wish to quantify from the point of view scattering coefficient, absorption coefficient in the broadband of wavelengths, you can use some integrated sphere, more comprehensive spectrometers, and to get these numbers. Also for in vivo study or ex vivo study, but mostly for in vivo study, you can use some optical coherence tomography system, which are available in any clinic now all over the world. So also together with the optical clearing agent, you can use some nano composites like gold nano particles to enhance the visibility of the any pathologies within the tissue, or to show the pathways of the delivery through the vessels or lymphatics and so on. So another point that we found that our clearing agents, in addition to the to see in depth, they give us the diffusion properties, molecular diffusion properties. We can detect how molecules which are used for clearing also give us information about their diffusion time. That means that we can test some pathologies like systemic disease, like diabetes. So we test it on the in the animal model, and we produce some alloxan, so-called alloxan induced diabetes. Use these techniques for to prove this idea. Once again, collimated transmitters, quantification, and also CT for in vivo. And you see here results that we have the collimated transmitters increase. This is diffusivity, real diffusivity of molecules. In that case, different concentration of the glucose. And this is diabetic skin, which was tested. It is samples, it's ex vivo data. This is for the control or normal animals, and this is for diabetes group. And you see here that we have quite different time of diffusion. It's a small prolonged for diabetes. And this is due to cross-linking of the collagen due to glycation of collagen within the tissue, and it's more tissue became more dense and less penetrative for molecules. So it's easy to estimate this diffusion coefficient and then to recalculate for the so time diffusion, recalculate to the diffusion coefficient of permeability coefficient. So the main idea is to measure diffusivity of molecules, of probing molecules for external organs like skin or mucosa, oral mucosa, for example, and internal organs like heart muscles or some skeletal muscles or other important organs. So we compare here the control group, a diabetic group, for here for skin, and proof that the diffusivity is less for the diabetic group. You see here numbers. And now we compare with the heart. The myocardium. This is once again for skin. And this is the time scale you see here. And also for the same is for heart muscle, red myocardium. So we have well differentiate the phase of tissue glycation in organs when the measuring the time response of the diffusivity of the external organs. So once again, this is numbers for another probing agent like glycerol solution. We see here quite good difference for skin and a correlation for myocardium. And this is the real numbers of the diffusion coefficient, which can be used for drug delivery, for example, for calculation how much you have to give agent with the same molecular weight of shape and so on. So this is results of in vivo measurements. You see here the OCT images for control group and for diabetic group. I would like to pay your attention that this is the penetration depth of light here. And for diabetic group, we see systematically more penetrative. Even why? Because we have a lot of glucose in the body, and we have already reflective matching within the diabetic tissue, within the diabetic animal. And after that, we put our probing agent, and you see that much faster they penetrate in 5 minutes. You see here, we have the good optical clearing and less here. So if we put or collect some numbers, you see here differences for control group for skin and myocardium. It's well decoded, 3, 4, 5 time difference. So very, very easy to differentiate this pathology. So also very important to move technology, optical technology to the deep ultraviolet. Why? Because some technologies like Raman spectroscopy and imaging is very important technology which suffer from low penetration depth. But optical clearing is very effective here. Why? Because we have a high scattering here. Indeed, absorption is also high. Therefore, the penetration depth is small. But please pay attention to this graph. You see here, this is the 0 time, this is 30 minutes time, and this is collimated transmittance in the ultraviolet. This is 200 nanometers. Indeed, collimated transmittance is very small. But after optical clearing, we can increase it up to 20 times, up to 20 times. So indeed, we have a huge photons which are enough to use any technology, imaging technology or spectroscopy technology, which are using the photon counting system. So the efficiency up to 1000%, and this response, this spectrum, this dynamic spectrum reflects the gains between the DNA concentration and protein concentration. Very, very, very important from the point of view of prediction of malignancy of tissues. So the same for oral mucosa, for gums. You see here, this is another technology. It's the back reflectance, not transmittance, back reflectance. Also, we see less scattering. Therefore, some with time we have decay of the back scattering, That means that we have some refractive index matching and so on. For samples, in transmittance also we have increase here, new window here. This is window, and this is bands belongs to the proteins and to DNA. So much more improved optical window in this also very important wavelength range from 300 nanobits for 400 nanometers. Also, this allows us to apply some ultraviolet treatment technologies, and we did it for the some disease of mucosa. I also would like to pay attention that electronic cigarette vapor liquid, it contains glycerol with propylene glycol. Propylene glycol is a good enhancer of the penetration any molecules, and also glycerol like refractive index matching material provide these windows and efficiency of optical clearing, indeed not only in the ultraviolet, also in the visible and near infrared. And this allows us to estimate the diffusion coefficients of this electronic cigarette vapor liquid. Also, we are working now with the lungs, because it's important how this this agent penetrates through the very thin membranes in lungs. So this is demonstration how we can use MRI contrast agents like Gadavis, Magnivis, Datarem. All of them are allowed for application in biomedicine. So you see here very good efficiency. Also, you see increase of the collimated transmittance. Also, OCT in-depth optical clearing, also not bad. Indeed, glycerol is better, but now you have two-in-one. You have you can provide some MRI contrast and optical contrast, so you can provide some multimodality approaches. So another point, very important, that to measure a diffusion coefficient of the any contrast agents, this is very expensive to use MRI. From one point of view, this is very comprehensive instrumentation. From another point, it's very slow. So we can apply very simple measurements in optics, and to get the same data, moreover, we can estimate not only the diffusion coefficient, but also tortuosity coefficient, which characterizing the length or diffusion of these molecules, of clearing molecules within the tissue due to its structure. So also fluorescence, such modalities, optical modalities, very popular in biophotonics, like fluorescence intensity. You see here, this is the tumor image of this this tumor of the mouse. And you see here image of this tumor. It is some cancer cells here before optical clearing of skin and after optical clearing of skin. Much more contrast and much more detected cancer cells. So this is some details showing that we can improve not only we can count these cells, but also to see behind these fluorescing cells and to improve some contrast. So it did for a few mouse here to have some mice to have some statistics. So this is the first demonstrations published a couple of maybe 1 month ago. We demonstrate that we can detect both concurrently the fluorescence image and also MRI image using the gadobutrol, the same contrast of the tissue. This is before clearing, this is after optical clearing. So also recently published paper, we demonstrate that the fat tissue also can be optically cleared in vivo. So this done in vivo. You see here before clearing, this is the fat pad of the tissue. This is the after 10 minutes of the optical clearing, and then you see nothing. Why? Because no scattering. So this is before optical clearing, after optical clearing. Indeed, we try to understand what has happened with the cells and to provide some more optimal protocol. We measure the scattering coefficient reduction you see here in time. And for us, it was very important because this work was ordered by the Olympus company. And recently we published this paper together. We have a patent and so on. This is a work needed for some surgery because robotic surgery, when you are going in different tissue and you may cut some important vessel. And if you put some clearing agent for a while, you will see better using some imaging, optical imaging modalities. So indeed, Raman also can be improved. Now we are working with enhanced Raman, CERS. Also very, very good results. This night I check up my work of my students, and they did very, very nice work with the optical clearing of skin and to see some surface enhanced images behind the optical clear. It's very, very clear spectra. So also it works well for optoacoustics imaging, for optoacoustic angiography or lymphography. And very important for any photoacoustics technology, they also use sound matching agent like sound jets. Yeah, they are also optical clearing agents. We can replace, for example, water or sound gel by glycerol as we did, or make a mixture. As you see here, 70% of glycerol, 30% US gel. And now we have both matching in ultrasound and in optics and see much, much better images of the vessels. So optical clearing, this is demonstration of optical clearing of blood. And blood, we have some sample of blood. This is slide of blood with some melanoma cells inside. Nothing seen spectrally, but after optical clearing, you can enhance a few times, 20 times the sensitivity for detecting with these melanoma cells on the background of the red blood cells. So also it's very important, and we recently published a review paper in Advanced Drug Delivery Reviews on the how to reach by light to detect or to kill bacteria in many different situations, like pockets or tensular tissue, hair follicles, and so on. So after optical clearing, you can see in depth and also to treat using photodynamic or photocatalytic technology for these germs. So also
we've got
this,
about 2 minutes left.
I'm finishing. So this is also examples how to do it in the Falix, here Falix. You see here some drug delivery and also enhancement. And we have to see where we put our capsules. So, and the last maybe example how optical clearing can help for laser-induced breakdown spectroscopy. Indeed, it's happened due to better focusing, no blurring of this beam which are producing plasma. So also we need some phantoms, and these phantoms, porosity phantoms, give us information how we may clear the lung tissue, for example. And it works well because refractive index matching and dehydration also work. And we can check up without real tissues many of chemicals. So this is final maybe slide. We published recently a few books on the optical clearing. This is diagnostic of cancer, but also which is very helpful for cancer diagnostics, our technology. And this book, handbook on tissue optical clearing, now also available. So I would like to say only that optical clearing technology is very beneficial to enhance multimodal spectroscopy, imaging, and treatment. It is very, very applicable for many different kinds of the optical, and not only optical, but also X-ray, computer tomography, MRI as well. So we are well integrated in the international collaboration in this field. And you see here our group and also groups in China and all over the world. So we also have our own meeting, and you are welcome to attend this meeting this September. It also will be in two modalities. It's online and offline. Thank you for your attention. I'm ready to questions.
Thank you very much. This is a very interesting talk. Thank you. Are there any questions? I'll check the chat, or if you would like to ask a question, you're welcome to unmute yourself or raise your hand. And we have time just for one question, and then we'll move to the next session.
No questions.
Well, if anyone has any questions that they think of during the day, please just, I'm sure you can post it in the chat. And yeah, so thank you very much. Thank you very much for the interesting talk. We're actually not going to break for the coffee break now, so we're going to go straight into the next session. But I'm sure if you want to grab a quick coffee, just get something quickly and then come back. So we're going to move over to the next chair in the next session. So thank you.
Thank you very much. Bye.
Thank you. Bye.
Professor Mustafa Muradov, are you here?
Yes, I am here. Now I will begin.
Yes, hello, everybody, welcome, good morning. I am from Sivas Cumhuriyet University Physics Department, Professor Dr. Ebru Şenadım Tüzemen. Today is the third day of the Congress. We are now in the second session. There are 4 presentations in this session. Now, invited speaker is Professor Mustafa Muradov from Nano Research Center, Bakü State University. Title of presentation is Nanowires on base of silver-2 sulfur, synthesis and optical properties. Okay. Can you share your presentation, please?
Yes, now I will be share my presentation. Oh. Peki dokumentten geri söylüyor.
İmkan vermiyor o açma bunu basabilmem lazım. Biz koşulu siz dediği orada eləyir. Biz koşulu
Bir dakika. Belki cannot yoksa.
Oydu cannot.
Belki bunu da dedi. Okay. Document burada.
Sizden gibi okursun aşağı. Gerçekten var.
Belki siz başlayasınız da. Oh. Belki
Desktop'a basın, şehre basın bir daha. Şehre basın bir daha.
Basırım mı? Gitmiyor. Orada.
Privacy.
Ha.
Click buna basın. Use password basın.
Onda pasport.
Bilmirsiniz use password'unuzu, Apple ID'nizi. Parmak iziniz var, koyun parmağınızı oradan scan edin. Daha çıkıp koyun bura. Bura. Böyle. Olsun. Görürler. Ha, görürler. Açın, значит, keynote'umuzu. Did you see our screen or?
I see only to you.
Ah, okay. Now you see our presentation.
Yes, we see.
Okay, let us begin our presentation. First, excuse me for this problem with connected with internet. And today I will be told about our laboratory and process of synthesis Argentium nanowires and preparation silver sulfate hybrid nanostructure. Our laboratory consists from 20 scientific workers, and main direction of our research is triple nanogenerators. One groups, our research group works with triple nanogenerators. Other groups working in area supercapacitors on base of various type of nanomaterials, and third groups working in area creating of biosensor. All these group needs for flexible conductive element, and such conductive element maybe silver nanowires, and we use it for synthesizing of silver nanowires, Payol methods. And after synthesizing, we also doing modification of these nanowires by reaction silver nanowires with sulfur ions. This modification allowed the change of band gap of surface structure. As you know, the band gap of bulk crystals of silver sulfide is around 1 electron volts, but band gap of silver sulfide nanostructure, you can vary it in wide energy diapason from 1 electron volt to 4.3 electron volt. And in process photocatalysis, this is important, which range of energy spectrum you are using for carrying out photocatalysis process. What we use, as I noted, Payol process for synthesis of silver nanowires. This process was described in this article, Chemical Society Review. And as a reagent for synthesis, we use polyvinyl prolidone, calcium bromide, sodium chloride, glucose used as slow reduced agent, silver nitrate, ethylene glycol, and ethanol. This is a device which we use it for synthesis of silver nanowires. The oxygen removed from system by help of neutral nitrogen gases. There was showed the process of growing process of Argentium nanowires. We used silver nitrate, polyvinyl prolidone, glucose, initially for reducing of silver ions. In first going reduction process, after the nucleation process, and the next process is formation of nanorods and growth of nanowires. The polyvinyl prolidone helps to get wires structure. Here we show X-ray diffraction pattern for such structure, and we show that in result this process we forming the silver nanowires. Here we show optical microscopy image for such structure, and we do also scanning electron microscopy investigation such structure. The length of but diameter of such structure was dependent from reaction parameters and changing from nanometer. Analysis of structure, you can see here that we have reflex also from other elements, silicium and aluminum. This is reflex from substrate structure. This is TEM image of receiving structure, and as you can see from this figure, the diameter of this wire is about 40 nanometers. This is absorption spectra of getting structure. Here we can see two maximum from argentium nanowires. One, this is connected with plasmon oscillation spectrum. If in left part, this is oscillation from longitudinal frequency of plasmon and nanowires. Here showed the same image, initial argentium nanowires and argentium nanowires, which was modified with help immersing of such nanowires to sodium sulfide solution with different concentration. As you can show from this figure, in this case, the morphology of modified nanowires also was changing, and this changing depending from concentration of sodium sulfide. Here also we showed mapping process, and from element mapping you can show that the image for silver atoms and sulfurs atoms are same, and this means that the quantity of such atom and structure was same. Here showed the results of X-ray diffraction from structure silver nanowires and silver nanowires after modification in solutions in sodium sulfide solution. And on right part, we showed the dependence of absorption spectra from wavelength. And here we showed the dependence of band gap received silver sulfide structure from hybridization time. And as we can show from this figure that depending of hybridization time of modification, surface modification of silver nanowires, the band gap of structure was decreased. The changing of this band gap will be depending from concentration solution, the volume which we used for modification of wire and the quantity of sulfur ions in used volume. Because this is interesting to investigate dependence this process from dependence from this process from concentration of used solution. We showed the dependence of absorption spectra from wavelength and solution of sodium 0.01 mole. And this process we also can use as diagnostics process of such kind of structure, and we now the absorption spectra modified elements, and with changing of this spectra we can estimate the degree of transformation this structure. Here showed the absorption spectra for silver nanowires and silver nanowires after transformation in sodium sulfide solution enduring 90 hours and concentration solution was 0.01. And we showed various the absorption spectra for various concentrations various time in limited volume. Side we can show spectrum in various time for concentration 0.001 mole, but in right side showed the modification of silver nanowires in sodium sulfide solution with concentration of 0.01 mole. We can see that in limited volume, if the quantity of sulfur ions limited, you can form the thin films on surface area of nanowires, and you can control by controlling of concentration of sulfur ions in solution to control it, the thickness of forming layers. And in case of low concentration of sodium sulfide, you can form it thin layers, and you don't destroy silver nanowire structure. When you increases the concentration of sodium sulfide solution, the spectrum change more, and this spectrum like to spectrum silver sulfide spectrum. And we showed that when we increasing concentration and wire structure destroyed, and we getting silver sulfide nanoparticles. Here also we showed the process of transformation from transformation of structure and from time of modification process. This is interesting that when you changing concentration or to modify it with plasmon oscillation. Plasmon oscillation frequency is dependent from electron concentration, but and with changing of these materials, surface materials, we also changing the concentration of free electrons, and this will be also influenced to maximum of plasmon oscillation. And here we showed the maximum of plasmon oscillation depending of modification process for low concentration of sodium sulfite. In low concentration, low sodium sulfite, we can show that with changing of the time of modification does changing. We also this changing also may be connected that the changing of, if you have a solution with which consisted ions, and this ion will be interacted with electrons in volume of nanowires, and this will be changed the potential energy of charge carriers in nanostructure, and this will be also changed the energy spectrum of the charge carriers in limited area in nanostructure. And in conclusion, I want to say that this process of changing spectrum and modification process, we also can use as indicator of changing of chemical composition, because other methods of controlling growing or modification process is difficult, but with help optical methods we can controlling the growing process of transformation and growing process. Thank you for attention, and this is my presentation. Thank you.
We thank tonight your presentation, Professor Murado. Do you have any question? Do you have any question? No. No. Thanks again, Professor Murado.
Thank you.
Thank you very much. Yes, next speaker is Mohammed Bakirov from Nano Research Laboratory, Bakir State University. Title of presentation is Dependence of the Optical Properties of Composites based on GO on the annealing temperature and filler concentration.
Hello, everyone.
Hello.
I am sharing my presentation.
Yes. You can share your presentation, please.
cannot share our screen. You can enable us to share it. Are you hearing me?
I don't see.
We want to share screen. They're writing. Okay, thank you. Did you see our screen?
Yes,
Ah,
we can see. Okay, you can begin, please.
I am Mehmet Bağırov. I am first year master degree student in Baku State University. My talk title is Dependence of the optical properties of composites based on graphene oxide polyvinyl alcohol on the annealing temperature and failure concentration. Recently, extensive research has been conducted on the development of graphene oxide. Graphene oxide materials and new types of composites based on them. These type of materials have a wide range of applications in various industries. They are used in energy-strong device, in the development of supercapacitor, in creating various types of sensors, in the process of photocatalysis, and so on. Such kind of materials have a wide range of applications. The ability of means their physical properties through modification allows them of expand their applications area. So, dependence on the degree of reduction, it's possible to control the band gap of graphene oxide in the range of 0.02 to 2.2 electron volt. One of the most widely used materials, graphene oxide, have based composites. These types of composites are perspective materials in the manufacture of supercapacitors batteries. Therefore, the stability of these materials to various influences, the development of their optical, electrical, and other properties on the temperature is of great interest. In this slide, graphene oxide was obtained by Hammer's method. For scientists of graphene oxide by this method, graphite and sodium nitrate were added into solution sulfuric acid and stored in the ice bath. Calcium permanganate added slowly to the solution, and stirring process is continued for 3 hours. The solution color became dark green. The yeast bath was removed, then stirring was continued for 1 hour, and the temperature was maintained at 35 degrees Celsius. Then distilled water added slowly and stirred for 1 hour. At this time, the solution color became brown. Then distilled water added directly and stirred for 1 hour. In the end, hydrogen peroxide was slowly added to the solution, and solution color became dark brown. The obtained sample was filtered through filter paper, washed several times with the hydrogen fluoric acid, 30% concentration, and distilled water. Graphene oxide dried at room temperature and then was added to distilled water. The solution was exposed to ultrasound for 1 hour and 10 centrifuge. The precipitation was dried at room temperature. Graphene oxide with different concentration, such as 1, 2, 3, and 5% concentration has mixed with polyvinyl alcohol and dried at room temperature. The obtained graphene oxide polyvinyl alcohol-based composite was subject to thermal treatment and different temperature, such as 25, 40, 70, 110 degrees Celsius. Absorption and transmission spectra of samples were recorded with the score 205 plus device in the wavelength range of 190 nanometer to 1100 nanometer. Here, transmittance spectrums for polyvinyl alcohol films with different concentration of graphene oxide are shown. The maximum transmittance was observed for graphene oxide polyvinyl alcohol with 1% concentration. It is 14.78%. Transmission dependence of wavelength at different temperature of graphene oxide polyvinyl alcohol composite films at different concentration is shown here. The maximum transmittance was observed for graphene oxide polyvinyl alcohol with 2% and 3% concentration film and dried at room temperature. According to Taklov, graphs were plotted and the temperature and concentration dependence of the band gap was determined. The band gap value of the samples decreases with the increasing annealing temperature of samples. When samples are annealed at 110 degrees Celsius, the change in the band gap for a graphene oxide with a 2% concentration is 0.50 electron volt. Whereas for a graphene oxide with a 3-point concentration is 0.5 electron volt. Most likely, this is due to change in the particle size as a result of collision process, and increases in concentration to 3% entirely increases the value of the band gap, 2.55 electron volt. The next increases in the concentration of graphene oxide nanoparticles. 5% concentration leads to the decrease in the band gap, 1.18 electron volt. This is due to decrease in the distance between the particles and an increasing in the probability of aggregation process. Thanks for your attention.
We thank you, nice presentation. Yes, have you any question? Yes, have you any question? No question, I think. Thank you very much again. Akiro. Thank you very much. Yes. Next speaker is Keshan Singh, School of Physics, University of the Witwatersrand, South Africa. Title of talk, Encoding Information into the Classical Non-Separability of Light.
Okay, hello. Are you able to hear me clearly?
Can you share your present? Yes, you can.
And can you see my slides?
Yes, we see.
Okay, great. Okay, good morning, everyone. My name is Kishan Singh. I'm a PhD candidate at the Structured Light Laboratory based at the University of the Witwatersrand in South Africa. And today I'm going to be speaking to you a little bit about the classical non-separability of light, how it is invariant to certain types of transformations, such as those through those transformations when propagating through turbulent free space, and why this is useful for certain applications, mainly encoding information. So to begin with, as many of my colleagues have already mentioned, we can structure light's various degrees of freedom. So we can structure light's amplitude and phase, and we can understand this in the context of scalar spatial modes of light, which are solutions to the paraaxial Helmholtz equation in different coordinate systems. So in cylindrical coordinates, we have the Laguerre-Gaussian modes. In Cartesian coordinates, the Hermite-Gaussian modes. And there are also propagation invariant solutions like the Bessel-Gaussian modes, amongst many others. And we can also structure light's polarization degree of freedom, as Dr. Angela Dudley was speaking about yesterday. And we can understand this in the context of vector fields or vector modes of light. And a nice way to interpret these vector modes is as superpositions of scalar modes, such as the Laguerre-Gaussian modes with orthogonal polarizations. So the R and L here represent the right and left circular polarization Jones vectors. And we can see that when we take this superposition, we end up with a polarization profile which varies in the transverse plane. So it's inhomogeneous in the transverse plane. And depending on the constituent modes, this polarization pattern changes. And we have various ways of generating and detecting these types of modes. So for the work I'm about to present here, the way the modes were generated was by using a laser source, a helium neon laser, and then with a quarter wave plate and a Wollaston prism, two orthogonal polarizations of the Gaussian mode produced by the laser were separated, and then they were recombined and shaped independently. So the Laguerre-Gaussian complex fields were encoded into the orthogonal right and left circular components and combined interferometrically using a single element, in this case, a digital micromirror device. The desired information was encoded into the first diffraction order, which was isolated using an aperture at the focal plane of a lens. And if you'd like more information about the specifics of how to generate these modes and how to detect them, you can look at our recent nanophotonics paper. So there have been some attempts to understand these vector modes and if they could present some benefits over their scalar counterparts when used for communication through atmospheric turbulence. So a lot of these older studies utilized metrics which didn't necessarily account for the polarization structure themselves, but rather the total intensity. So in this work, the authors used a scintillation index, which is a measure of how much the intensity profile varies. And they noticed that as they propagate further through atmospheric turbulence, the scintillation index or the variation in the intensity for vector vortex beams decreased more than their scalar counterparts. And these authors used this to argue that this represents some form of invariance or benefit of the vector fields over their scalar counterparts. Some other work also utilized a signal to noise ratio, once again, only dependent on the total intensities and not the structure. And what they showed was as the turbulence strength was increased, the signal to noise ratio for beams containing C-point singularities, which are just special types of the vector fields I mentioned earlier. And they noticed that for these beams, the signal to noise ratio drops it decreases much more slowly than their scalar counterparts. And these authors also use this to argue that this represents an advantage of the vector fields over their scalar counterparts. However, when the actual structure, the polarization structure was taken into account and information was encoded into this set of 4 orthogonal vector fields and turbulence was introduced into the system, crosstalk was observed and the distortions in the polarization structures resulted in the information being lost when turbulence transformations were introduced. And the reason for this was that propagating through the turbulent atmosphere represents a one-sided unitary transformation. And we can start to understand how this affects our vector light fields. So if we have our constituent scalar components, we can notice that these scalar components are orthogonal. We can't factor anything out of them, and the polarization states are orthogonal. And when we take the superposition, we get our vector structure. And we can take this structure and transmit it through a variety of different one-sided unitary channels, such as transparent cellular material, underwater channels with varying refractive indices, birefringence and optical fibers, which acts on the polarization degree of freedom, as Dr. Isaac Nape was mentioning a couple of days ago, as well as atmospheric turbulence. And the atmospheric turbulence will affect the spatial modes and distort them quite severely, which leads to a subsequent distortion in the vector structure of our beam. And even though it might not be necessarily clear from these images, since the transformation is unitary, the orthogonality between these components is actually preserved. And this means that the non-separability between the spatial and polarization degrees of freedom is preserved through these one-sided unitary transformations. Now, how can we start to understand this non-separability? To do that, we can make use of a graphical tool, which is called the higher order Poincare sphere. So this is a sphere similar to the Poincare sphere, but it's constructed with the constituent right and left circularly polarized orthogonal scalar components on the north and south poles. And if we examine a state on the north pole, we say it's completely separable. So this is just a right circularly polarized scalar Laguerre-Gaussian beam. And we can say that regardless of where we look spatially, we can always say it's going to be right circularly polarized. We don't need to define any spatial coordinate to know that it's going to have some right circular polarization. If we introduce the left circular component into the superposition with a lower weighting than its right circular counterpart, we notice the structure changes. And now, depending on where we look spatially, we have different orientation angles of the polarization ellipse. However, the ellipticity and the handedness of the polarization is the same regardless of where you look in the beam. So we can factor out the handedness and the ellipticity, but in order to know the orientation of the ellipses, we have to specify some spatial information. So we say that this field is partially non-separable. And if we have the case where our constituent components are evenly weighted, then we have a maximally non-separable state. We can't factor out any single polarization property without specifying where in the beam we are looking. So the spatial degree of freedom and the polarization degree of freedom are completely non-separable in this case. Now, we have a way to quantify this non-separability. So if we have our vector state of light, with our orthogonal spatial components, in this case, we're using the horizontal and vertical polarization states. You could use any two orthogonal polarizations. We can use a metric inspired by quantum entangled systems to characterize the degree of non-separability, and this metric is called the concurrence. And it can be shown that the concurrence is given by this simple expression here, which is only dependent on the inner products of the constituent scalar modes with themselves and with each other. And if we start to look at the effect of our one-sided unitary transformation on our vector field, we can understand this in context of what the transformation is doing to the scalar components, which is distorting them as we discussed before. And what this means in the context of the higher order Poincare spheres is that our transformation maps us from the old sphere onto a new sphere, which is defined by these new orthogonal spatial components. And if we want to understand what is happening accurately, we can't use the basis formed by the components on the old sphere, since the inner products will give us the incorrect values. And if we want to recover the concurrence, which we know must be preserved, since by definition, the unitary transformations are going to preserve these inner products, we need to account for the effect of the channel. So if we account for the effect of the channel when making our projective measurements in order to calculate our concurrence, then we reveal that we can measure the true inner products and therefore the true degree of non-separability. So these are some experimental results for an example unitary transformation through a tilted lens system, where if we generate in the original basis and detect in this original basis once the unitary transformation is applied, we measure no non-separability, which is incorrect. However, if we measure in our adjusted basis, we measure our complete non-separability again, since we now have the correct inner products from which to extract our non-separability. In the same way, we could send in an adjusted basis to compensate for the effects of the channel if we really wanted to measure in this original basis. And this is a very powerful tool for information encoding, because what we can do is we can define our orthogonal spatial modes with right and left circular polarizations. If we send it through no transformation, the information is preserved. But when we introduce our unitary transformation in the form of atmospheric turbulence, we can see that power is distributed across the spatial components. However, when we make our measurements in the adjusted basis, or we generate our beam in a compensating adjusted basis, we can see that information is preserved. And what we can then do is encode our information into an alphabet. So the combinations of the orthogonal scalar modes and the orthogonal polarizations make up an alphabet of information with which we can encode an image, such as this map of Africa. And as we send each pixel of information through our turbulent channel, if we measure in the adjusted basis, we can see the image is severely distorted. And for increasing strengths of turbulence, the distortion is exaggerated even further. However, in the insets, we can see the results of measuring in the adjusted basis. And we can see that in both cases, the correct information is recovered with quite a high degree of fidelity. So if you would like to read up more on this work, this QR code will link you to an old version of the paper, which is currently on archive. However, if you're willing to wait just a couple of weeks, it should be published in Nature Photonics very soon. These are some of our collaborators. In particular, this work was done in collaboration with some of our colleagues at the University of Glasgow. This is our team. So Dr. Angela Dudley, Professor Andrew Forbes, Dr. Wagner Tavares Bueno, Dr. Isaac Nape, Ms. Anne Kritzinger, who's from the University of Pretoria in South Africa, and myself all contributed to this work. And I'd like to thank everyone for their time, and I'd be happy to answer any questions you may have.
Thank you very much, Steve. We thank the nice presentation to you. Have you any question? Have you any question? Thank you very much again. Next speaker is Dr. Dmitry Kovalenko. Are you here, Kovalenko? Are you? No. He's not here.
We are currently having a network connection problem with next speaker. Thank you very much, Professor Şenadıl Tüzemen. I think.
Thank you very much.
Now time to lunch break. Thank you very much again.
Yes, thank you very much. See you. Bye.
See you.